All right, everyone. I have some great news. I solved the issue, right? We're having this problem. Some people believed light was a wave. I believed that it wasn't. And, you know, um, I had to do some thinking. Today I decided to do some pondering on the magnetic field. What is magnetism? And upon my consideration here, I have discovered that we can both eat our cake and have it too. And it's great because everyone's happy. So basically, I was thinking about magnetism and I was thinking, okay, well, what causes magnetism? Well, we know that magnets cause magnetism. Okay. And then we know that we can make magnetism happen with electromagnets, right? So between these two things, I was trying to think, okay, well, what's going on here? Well, I thought, okay, well, we have a magnet, right? And if you have two magnets of the same material, but different sizes, the bigger magnet is a stronger magnet. And I thought, more mass, stronger magnet. Well, that's interesting. Why would that be the case, right? So that's where I started. And I was thinking about how, we have, well, stronger magnet probably means, stronger force, right? This greater force is coming from, assumingly, like a flow of something, right? And basically, we look at these magnetic lines coming out of a magnet, right? And we see, if you look at like the lines, it goes out one side, comes in the other. And, two like ones repel each other, right? Because like poles repel and opposites attract. And the reason why that is because one is sending out the flow and the other one is pulling in the flow. And when you draw those without putting the arrows on them, right, you draw one side with inflow, right, on both sides, and one with outflow on both sides. Both of those lines look the same. So, what happens is that, if you really want to, you can make magnets touch, depending on how strong they are. Even if they repel, you can push them together, but you have to apply a greater force to do that. And basically, that means that, it's not like they do repel, but, water flowing out of a pipe, right, would seem to be repelling if you can't block it up, right? It's getting shot out with a lot of force. So when you have two things getting shot out with a lot of force, it seems like they would be repelling each other. And when you have, a lot of stuff flowing in, if you close it up, then nothing can get in. So it tries to keep a hole open if there's a hole open, right? So on the other side of the pipe leaking, right, there's a strong resistance with blocking up that hole with anything unless you put it over the whole thing and just block it up completely. Like if you just try and slowly patch it, that's not gonna work. And same thing with on the outside, you can't slowly patch it because the flow will just push whatever you're trying to build right out of the way. And so that was a bit of a long tangent. I don't know if that really cleared up my explanation there, but basically they both repel for that reason. And this flow that we're, building here is, as I've said, that charges, things like electrons, right, particles are constantly emitting and absorbing energy. And what's happening in the flow of a magnetic field is basically the electrons are being pulled into basically an energy kind of deficit sort of situation. I kind of described this when I was talking about superconductors, where the electrons basically get pulled in and they're just following the leader through. And so in a magnet, a similar thing is happening, right? Where these electrons are just kind of getting pulled in because, well, the electrons are trying to get out the other side as fast as possible. And so once they get in, they just are trying their best to get out. And the lower energy so what's happening in a magnet, right, is that on one side of the magnet, what's there is the outflow of the electrons. So the electrons are moving out into a higher energy zone. And so the electrons fly out that side. But what happens is once an electron is at the very end and it flies out of the magnet, okay, well now whatever electron was next up in line, the point with the most energy is going to be in that direction as well. And so it moves down, and then the next one after it is like, oh, well, there's more energy over that way because there's less particles in that per area, right? So it moves into that empty space that was made by the last electron moving down, and you get this like chain of electrons following the leader basically right out the other side, because once an electron gets pulled into this, they they have no choice but to follow it through. And then what's happening is basically you get these magnetic lines that we see where these electrons are getting shot out, and depending on, which line they're on, they're all relatively in line here, but as you go out, it kind of loops around and comes back in, and they get wider and wider. And I think what's going on there might have something to do, and basically we'll go back to what is happening is that these electrons are absorbing dark energy, right? And so inside the magnet, there's less available energy. So they want to get out of the magnet. But once they get out of the magnet, then some other electrons have to flow in. And so we get this kind of magnetic loop. And when you put down the iron filings, right, they form sort of a line, sort of these lines following this direction, because all the electrons are kind of flowing in this loop around the material. And you can see this, like every particle is considered a tiny magnet, and it's because these like the particles on the individual level are doing the same thing. They're absorbing in energy and sending it out, and so they are creating these energy differentials themselves. And so you get, it's different scales, of course, but that's why an electron is a tiny magnet, and all the particles are really just tiny magnets, because what they're doing is they're taking in the dark energy that is everywhere around us, and when they take in that energy, then there is less energy in that area, so the dark energy flows in to fill it. And this flow is the kind of thing we see, as well, gravity, but it also affects what magnetism is. And I kind of jumped the gun there a little bit, but basically what I'm getting at is that gravity and magnetism may be one and the same, because what's happening with gravity is that everything is following the flow of energy, and what's happening with magnetism is that basically the particles are reacting to higher and lower energy. And so when there's less energy, they go, oh, less energy there. I'm going to move, I'm going to move towards an area with more energy. And then that kind of creates this global effect, because there's not just one particle in space, there's like trillions of particles in space. So for if one particle moves, it causes the other one to have to move, because it's constantly changing the energy balance of space, right? And so what is happening is we end up getting this flow of electrons flowing in and out of the magnet, and and so from there I was like, okay, well, we look at electromagnets, right? And so when you have an electromagnet, like inside the coil is the stronger current, because there are more. And why would that be? Well, that's because inside the coil there's a concentration of emitted photons, because we know that running electrons through a wire causes the wire to emit photons. How do we know this? We know this because of light bulbs. We know this because wires heat up over time. Heat is infrared light, and so infrared light is photons. And so we know that we are emitting photons when electrons get run through a wire. And the faster you run electrons through that wire, the more photons are emitted. And I could be wrong, but I'm pretty sure the stronger the magnetic field. And why is that? Because all of these photons are getting emitted into this concentrated area, creating a large, and they're absorbing the energy as they get shot out, right? And so as they absorb the energy within the coil area in larger and larger amounts, it is increasing the amount, it is reducing the amount of dark energy within that zone. And so it is creating a energy differential, basically. And so electrons flow out of there, but when electrons flow out of there, then, well, there's no electrons there, so that becomes a better location for energy. But then all of a sudden they flow in, they're like, oh, well, this looks like a good way to go to get more energy. But then they fall in and they realize, oh no, it was a trap, right? And now they were following it, but now the only direction they can choose to go, because they have electrons following them, is to continue through. And so you get, the electrons will follow the path thinking they're going towards the point of more energy, until they realize that they're not. But by that point it's too late, and so it still is the point of more energy for them, so they have to keep flowing down, and they flow down and through the coil, and you get this kind of flow through the coil, and that results in your magnetic field, basically, because again, these lines of where the electrons are flowing gets farther and farther and weaker of a flow, because the larger the distance, the slower it flows, because the more distance you have to travel, and before you get back in there, pretty much. But I think I'm getting a little too into detail. Either you understand what I'm saying right there or you don't. I'm going to move on. And so I was like, okay, well, running, considering that, right, if, considering that, so we know that emitting photons inside the wire, that creates a magnetic field. Well, what else emits like a large amount of photons? And so I was thinking lasers, right? A laser emits a large amount of photons. These photons should then absorb large amounts of energy, right? And lo and behold, I looked it up. I mean, you can look it up yourselves. Basically, there was a study talking about it. I didn't read the whole thing, but they were talking, like, I guess I could look into it more, talking about magnetic, what did they call it? They called it like magnetic friction or something. And I was I didn't really look into that much to see what that phenomenon is about, but they were talking about magnetic friction, and they were doing this study about shooting pulses of a laser and noticing this magnetic field is generated, and it kind of lingers a little bit longer than the pulse is there. And this is interesting in itself because this points towards what I'm saying. Well, one, a pulse of a laser, right, is creating this magnetic field for the same reason that I'm saying, right? It's absorbing the energy and creating an energy differential, and so you have the beam of photons going out, and then you have your magnetic field force. Hold on, I'm getting ahead of myself. I have a drawing to explain what I'm talking about there. But, and then it kind of lingers. And this is an interesting thing. I didn't look a lot into this, but the fact that it lingers would point towards it not being caused by the electrons, right? It lingering longer than, if they're using electron lasers, maybe they're using like an electron, like a free electron laser or whatever. I don't remember. I don't know for certain. I don't think they were. I think they were just using like a high-powered laser. But, technically not really any electrons involved in that, so there shouldn't be a magnetic field, from my understanding, or at least not like a strong one, because we know it's an electromagnetic wave, but I don't know. Maybe I'm digging a hole for myself there. I'm going to ignore what I was saying with that. But basically, it lingers because this energy differential takes some time to go away. And so, even though the photons that absorb the energy have moved on, there's still a difference between this point and this point, and so we still end up with this kind of magnetic field lingering for a little bit. It's probably not very long, granted. Like, it's not like it's going to be there for 20 minutes after the laser is gone, but it's there, because the energy in that point is still lower than what is around it, and so it lingers a little bit longer than the pulse itself. And going on, so basically the fact that lasers do, like, my hypothesis was like, okay, well, lasers should also generate a magnetic field, and they do. And so I think that kind of backs up my claim here. But the alignment of spin is the sending of electrons into basically follow the leader kind of state. And this causes them to just flow in the direction of wherever they think is going to be less energy. And when you have two charges, you have a charge going out. We know we have the electric field. If it's going this way, then the magnetic field is like the opposite of it, right? So we have the path, we have the electric fields going up, and then we have the magnetic field. So I guess we could say that one of the, like, if you you would draw, it would be like this, right? So you got your force, which is the electric field, the direction that you're traveling, which is this way. So this is your force from the electric field. This is the direction of the magnetic field, right? So when it's flying out, I'm flipping you off. When it's flying out, right, the direction that the magnetic field goes is that way, right? We get a perpendicular motion for all of these like particles, right? We know that the result of this is perpendicular motion. For the magnetic field creates perpendicular motion, right? And so the reason is because, well, if the particle is flying this way, right, and the other particle is here, right, it's flying this way, the particle's here, well, it doesn't want to go this way because, well, this is absorbing energy, and so there's less energy this way, and it's not going to go this way because it's just going to get in the path of the particle, right? And so it can move to either side, and when it does that, that is going to put it in the optimal position for the quote-unquote best energy. Like there's going to be more energy over here than here or here, so it moves in that direction to just kind of stay in the best position for itself. And kind of going into that, we imagine I've got what I've resulted in here is that, okay, if that's the case, well, then we would have some kind of wavy motion result from this, right? And so then I'm like, well, crap. I just was saying, hey, it's not a wave. And then I come back to finding out, oh, maybe it is a wave. But here's the thing. Particles, like I was right. All right. But there is a wave aspect. All right. It's not the light itself that's a wave. What is a wave is the magnetic field that is created from the light. And so I can see why there would be some confusion here. But what's happening is I did a little drawing here. So I'll get up close and try and explain my drawing. Basically, we have our particle right here. This is our photon flying through, a bunch of particles in space. And so all the particles that are going to be the closest to it, right, these ones, are going to want to move away. Because this one, I drew it as if it's like shining, but I mean, it's a photon, so it kind of is shining. But it's also absorbing energy as it goes. So as it goes along, it's absorbing the energy in its path. And so these ones are like, well, I need to get out of here, so they move this way, right? But then this particle here is like, wait a minute, this is too cramped for me, so they move out of the way, right? And then the next one goes, hey, wait, I'm cramped here, and they move out of the way, and so you get this path of the photons all just kind of pushing each other along to try and get to a point of more energy. And then what happens is after, I didn't draw it out here, but after this particle passes, all of a sudden this particle goes, hey, it's free real estate, right? So both of these particles on each side move back towards this point here, right? And they move towards each other. And then this one goes, hey, that looks great. So they move back up, right? And then, these ones again follow. And so you get then from the wave kind of moving out like this, and then you get a wave moving back like this, right? And then all of them will probably do the same thing again. If they, either they will or they won't. I don't know exactly how smart these particles are, right? So either they'll move too close, right? And then they'll go, this is too cramped. And then they'll readjust again, right? It'll kind of be like it'll dissipate. So the first one will be a strong wave, and then you'll get kind of like a little ripple before they all come back to equilibrium again and are happy. But the thing is once this wave moves out, over time, there's probably a slight loss in how much they move. And so that's why over a distance, the magnetic field dies off, because, they're shifting this way a little bit, and then this one shifts a little bit, and they all shift at less and less and less and less as you go farther away. So you get a weaker and weaker magnetic field or at a distance. But what's basically happening is that these particles are moving away from the point of low energy when it comes to the photons, and doing this creates if it's just one photon flying through, right? This is what it would probably look like with a laser. And again, you have your realistically, with the way this is like, this is the laser flying through, right? Your magnetic and force are both going to be basically the same thing, because it's going to be, you're going to spin around. So basically they're pointing, even though in this way they're pointing in different directions, right? When you spin, they're basically pointing in the same direction, because at any given point they're both enacting on that same point, just from a different, from a relativity standpoint, that force is being exerted on every particle around it. And so they all experience those two as one, basically. And so you could draw pretty much your magnetic field direction like this, and your electric field is this way, but really it's just the particle flying through. There's no electric wave, it's just the particle itself flying through. And then as you spin around, you get this magnetic field in all directions that is going to that would then I don't know what I'm trying to explain there. You would have your magnetic field, and it would create its loops, I guess is what I was trying to say. And the further out you are, the less effective, or the weaker the magnetic field would get, and as I explained, and such and things. And so basically, long story short, I think that magnetism and magnetism is a result of both the electric field and magnetic fields are results we see as the same thing, because they are the same thing, because they're both results of an electron or a particle in general emitting or absorbing energy. And my camera told me I was taking too long. It shut off on me. But basically they're the same thing because they're part of the same tendency of particles, and they both have to do with the behavior of particles with dark energy and what that entails. And going back to mass, right? So in like an electromagnet, the loss of the lack of energy is due to the high density of photons, right? But in a magnet, it is due to a high density of mass, but the material has to be conducive to creating electron flow, right? So not every material that is high density is necessarily very magnetic, but they probably would be, I guess, if they had electrons free to flow. I'm not sure. I'd have to look into the materials that are the best magnets and where they stand. And then compare that to materials of high density but low magnetivity. I'm not sure. I'd have to look into it. But I imagine it has to do with something along those lines. And so basically, in a magnetic material, the lack of energy is created by the structure of the tightly packed structure and density of the mass itself, which mass and energy are the same thing. So there's high energy, useful energy to us in the photons emitted, and there's high mass in the magnetic material. But again, not every material is conducive to letting electrons just flow through it, and so we don't see this magnetic property with other dense materials. But if all materials acted that way, then the denser materials would make the strongest magnets, if my theory is correct. And again, I don't know what what materials make the best magnets. I don't know where they stand on the periodic table, stuff like that. But if I was going to make a guess, that's what it would be. If that's wrong, then have to look into that and see what's causing that behavior then. But I'm pretty confident that will be the case, so I'm not too concerned about it. But yeah, pretty much, I'll admit it, I wasn't totally right. Alright, there is some waviness going on, but it is only magnetic waviness. There's no electrical waviness. It's just magnetic waviness. Yeah, that's not the light itself that's causing that. That is just an effect of the light itself is not waving. It's not magnetically waving. It's creating magnetic waves, but they are separate from the light. They are not the same. They're not they are not together. One is the cause and one is the effect. And I think that's an important distinction. And I know a long time ago we combined them together. And I mean, they both are relatively the same thing, but I do think that maybe they shouldn't be the same thing. And I also don't think that they should necessarily be considered forces anymore. I'm pretty much destroying all the fundamental forces. I think we're going to end up with the forces of, I guess, I don't even, I don't know. I don't know if you really need forces at all. I don't know if you need any fundamental forces. You know, there's high and low energy, and if you want to consider, well, I guess the only fundamental force is entropy. That's like an entropy thing, right? To flow from high to low energy. The fundamental force of the universe is entropy, period. I don't think I don't think you need anything else. Everything else is a result of that behavior. But I don't think that you need anything more than that. So, yeah. I think that's everything for this one. So, peace out.